see here is a two-storied, four-flat apartment building. From the outside, it looks like any other conventional building. So, what's special about this? It has been built much faster than conventional buildings. In just 1 month, it demonstrates the use of a green alternative technology, making use of industrial waste gypsum and glass fibers called GFRG panels, glass fiber reinforced gypsum panels. This building, which does not need any plastering, uses much less cement, sand, steel and water than conventional buildings. So for the same carpet area, the built-up area and the building footprint is much less than conventional buildings. Buildings up to 8 stories can be designed using this load-bearing system without the need for any beams and columns. In summary, the construction is rapid, cost-effective and green.
Government has launched 2 very important missions. One is Pradhan Mantri Awas Yojana Urban and second is Pradhan Mantri Awas Yojana Gramin. We need to construct around 30 million houses by 2022 if we want to provide Pakka house to each household in India.
Providing affordable housing is a formidable challenge in India. Our faculty and students have been working tirelessly on this, and today we have a technology which provides affordable and, more importantly, rapid housing using some very novel ideas.
What you see here is the stock of waste gypsum, 7 million tons of it, with an addition of 2,000 tons every day piled up into a hill awaiting disposal. It is this waste product of the fertilizer industry, reprocessed by calcining to make gypsum plaster, that forms the raw material for the GFRG panel. The panels manufactured at RCF Mumbai and FACT Cochin are based on the technology transferred through collaboration with Rapid Wall Building Systems Australia.
Big advantage of gypsum is that it has an initial setting time which is about half an hour. So in the factory we can pour a panel and half an hour later we can put it on the forklift and take it off the machine.
The panels are cast in 3 stages on a special table by pouring a paste of calcined gypsum and other chemical additives. Glass fibers are spread evenly onto the mix by means of a screeding and rolling process. Next, special aluminium plugs are inserted on top of the finished first layer with 20 mm gaps in between to form the hollow cavities in the panel. Now, the second pouring of the mix is done along with cut glass fibers with tamping to form the ribs of the hollow panel. After setting, which takes 25 minutes, the plugs are withdrawn and the casting table is rotated, and in its vertical position, the panel is taken out for drying by means of a special forklift. The drying of the panels is done in a dryer chamber in which hot air is circulated to dry the panel evenly for 90 minutes. After drying, the panels are cut using a computer-aided and automated process tailor-made to the specified requirements for any building project. It is important that all this information is carefully planned in advance and furnished at the plant site by means of cutting drawings to be furnished by the architect or engineer.
We realized that the same panel, which is 12 meter long as manufactured in the factory and 3 meter height, can be also used as a floor, as a slab. If you design it properly and reinforce it properly and fill the cavities with concrete. So you have small micro T-beams in the slab. Then we said the whole thing can be used as a building system with especially the joints also concreted with reinforced concrete.
The cut panels are then loaded onto trucks, keeping them in a vertical position using stillages so as to avoid any damage during transportation. We now see these trucks arriving at the IIT Madras campus and reaching the construction site. The foundation for the building is conventional in nature, requiring setting out and excavation up to depth of 1 meter below ground level. A levelling course of plain cement concrete is laid over the trenches and is subsequently waterproofed over the entire exposed surface. A conventional footing is constructed using fly ash blocks with a coat of waterproofing sprayed on all sides aimed at preventing capillary rise of any water into the building. A concrete plinth beam with reinforcing steel is cast on top of the fly ash blockwork. Vertical bars called starter bars are positioned inside the plinth beam to match with some of the cavities of the GFRG wall panels. Next, the superstructure work is taken up.
If you want to have a building system, there is a process you have to go through, especially if you wanted to certify as a building material. Initially, when the Australians thought about this particular system, they only used for vertical loads. Vertical loads means it takes only gravity loads due to its own weight, building's weight. We also have a large amount of earthquakes that can potentially happen. So we have to be very careful in understanding the building system's behavior when it is subject to lateral loads due to earthquake.
Based on extensive research carried out by IIT Madras, a structural design manual has been prepared and published by the Building Materials Technology Promotion Council, BMTPC, Government of India.
BMTPC is also operating a scheme called Performance Appraisal Certification Scheme. It is called PACS. Through PACS, BMTPC is authorized to certify any new building material and construction system for which Indian standard is not available. So all these new construction systems, they are not only cost effective but environment friendly, sustainable, safe, and they give a quality product.
Further, IIT Madras has developed earthquake resistant design procedures for use in different seismic zones in the country. On the first day of the superstructure construction, the wall panels are erected with the help of a crane. The panels are hoisted vertically and positioned in place over the starter bars jutting out from the plinth beam. Then, appropriate reinforcement bars are inserted as per the design into the cavities. In this two-storied building, every third cavity is required to be filled with concrete and reinforced with a 10 mm bar. Other cavities can be filled with any inert material such as quarry dust mixed with 5% cement and water. The vertical steel bars are tied to the starter bars and the verticality of the panel is ensured by using the plumb bob. Grooves are cut into the edges of the panel to facilitate integral bonding with adjoining panels. It is mandatory that all joints between connecting panels are filled with concrete and suitably reinforced with steel. The entire ground floor wall panel erection is completed in 4 days. The staircase work is also taken up using GFRG panels as the waist and landing slabs with reinforcement bars in all the cavities. Next, the work of casting the first floor slab is taken up. They are placed horizontally over the walls in different rooms. The ribs typically spanning along the shorter direction. Concrete tie beams connect the panels to the walls at all junctions. Every third cavity in the horizontal GFRG panel is cut open from the top and a reinforcement cage inserted to serve as a concealed beam. Further, a steel welded mesh is placed on top of the entire floor slab and is subsequently embedded in a screed of concrete 50 mm thick. The advantage with the system over conventional concrete slabs is that there is no need for shuttering and the finish at the bottom is excellent, not requiring any plastering. Also, the propping required from below at the time of concreting is minimal. Conduits for electrical work are kept in place before concreting the slab. After completion of the entire concreting in the floor slab, including the balconies and the staircases, the panel erection for the walls in the next floor is taken up and rapidly completed. Then, the GFRG panels in the roof slab are put in place along with the reinforcement at various locations. A 5-course waterproofing of the roof is done subsequently to ensure complete and long-term protection against any possible leakage.
So it's a sustainable technology, number one. Secondly, this technology have been studied in detail for more than a decade by IIT Madras. This technology is also suitable not only for single-story houses, but for a vertical stack-like structures up to 10 stories.
Time right outside that particular house designed by IIT Madras to provide housing for the poor, millions of poor people who don't have a roof over their head. I'm joined to tell us more about this by Professor Bhaskar Ramamurthy, the director of IIT Madras, and Professor Devdas Menon. This 2-bedroom apartment is costing less than 6 lakh rupees. Very tempting. Have you compromised on anything? How strong is it? How durable? How long can one use this?
No, we have not compromised on anything. In fact, it is very strong. From an earthquake resistance point of view, it's probably stronger than the buildings that are built today. From the point of view of long life, longevity, we believe it is as strong, as sturdy, and as long-lasting as any building that is built today. These kind of apartments can be used by you and me also. They look the same, they feel the same, and they are the same as any of the apartments we use. The only reason we say it's for the poor particularly is because of the cost reduction, the speed, and so on, that given the housing shortage in India for the poor, it can really tackle that problem.